Let us see the block diagram which is in this picture. As you can see, there is a plant, a second order plant, fairly easy to analyze. There is a PID controller. You can see that it has a 0 at the origin, and the reference is such that the initial value is 0 until 1, and then there's a step from time at time t equal to 1 for a final value of 1. And I just run my simple control loop. I know that because of the integrator, the steady state error, which is the block here, the steady state error goes to 0. The response of the plant is fairly nice. So you have a settling time of less than 2 seconds and a very small overshoot of 10% or less, and some corresponding control inputs. So if you see, the control takes values like very large, some 10, 20, and so on. If I just kind of ignore for this spike, uh, so if I instead put some constraint on what is the maximum a controller can deliver. Maximum in the sense, if I talk of a motor, the motor can deliver maybe a maximum current, sorry, a maximum RPM of say 500, or a battery can deliver a maximum current of say 1 ampere. So let's say here I put the upper limit of the actuator to be 5 and the lower limit to be a negative of 5. I run my simulation and see what happens. Uh, okay, so let's see what is, so this is my actual control input, which my controller computes, but the controller tells or computes the values that it should take so and so values. But since my actuator is capped at 5, it just stays here. It just cannot go beyond 5. Okay, and it just stays between 0 and 5, or -5 and 5. Okay, what happens to the actual output? What we see is that, okay, the output is slower, that the settling time is now between 6 and 7 seconds. The overshoot is about 15% and so on. And also we see the error curve is much larger than the original one. I go a step further and I put further tighter constraints to say that the actuator limits are now between plus and -3, and see what happens now to the output. Okay, so the actuator can only supply until the value of 3. The actual output now behaves inverse. So the response is slower. Overshoot is close to 20%. The settling time is 7 seconds, or it has increased a little bit than the previous one. The error curves are also have a larger area, and so on. Why is this kind of phenomena happening? Let us analyze that a little bit with the analysis that we know. Okay. We had in our previous lecture quickly talked about saturation in the inputs. So let's see what this actually means. So my standard control loop, if I were to draw quickly, uh, so has let's see, I have a plant here, a controller, uh, could be a PID, reference, output, error signal, and so on. So the output, let me call this as say U prime. U prime is which the controller computes, and it computes based on your rise time, peak overshoot, settling time, and so on. So let this be the U prime which the controller computes, and this U prime has terms uh, proportional to the error. This is a proportional controller. Derivative component largely based on E dot, and an integral component which integrates the error from 0 to tau, and so on. So suppose in a situation where say the error is constant, so this is my AE. For constant error, okay, this terms becomes constant. For constant error, this term goes to 0. But this term, what I see is it just keeps on integrating, right? So it just increases linearly. And for very large values, the contribution to u prime of e also becomes very large. It just increases linearly. And what we assume in the linear setting is that, well, this that the control law. Let's assume, for example, for instance, I'm only doing the integral control 0 to t e tau d tau. Because this increases with the area, this can take fairly large. So this is like a linear relation. Right? I just assume that, as this keeps going, that this is available to me. Right? So whatever is the value that u throws because of integrating the error multiplied by this constant. But in reality, if I say my motor can say have a limit of 500 RPM, okay, or my battery has a limitation of say 5 amperes, or if I have a valve, say it can have a opening of say in whatever scale, say 0.1 meter or something like that, which means that the relation between that the relation between the u prime and the e, because of the integrator, is not linear. Mathematically it is linear, but practically it is not. Okay, so let's say my u prime is say increasing like this, say at 100 rpm per minute. So this is my rpm. So here is my rpm. We say this is 100, 200, 300, 400, 500, and this is my, okay, whatever maybe the error. So as the error increases, I would demand an equivalent amount of control law. So this will be my u prime. Say my limit is say 300. Okay, so my control law will behave such a way that it will, until 300 it will provide me whatever I want. After 300 it just says I can't provide any more of that energy. I can also go in the negative. You'll say only a negative of 300 is allowed. Okay, so this is plus 300 minus 300. After this, whatever you ask for, my controller cannot provide, because that is what it is set to at its limitation. So we'll see of how does this affect my PID control, especially the integral part. Okay, so if I go here, say when the errors are close to zero, this person or this term becomes zero. This e dot is the has to also do with the derivative of the error. This has to do with the integral of the error. Let's say what happens if I subject my controller to some kind of an actuator saturation. So in the normal circumstance, say this is my set point that I'm tracking. My controller will act for a given peak overshoot settling time, which we can construct with the help of an appropriate zeta and omega n, and say I'm tracking a step. And say the control input, which my controller computes, is very well within the actuator limits. So this is my say 300, for example, and all my control inputs are over here. Okay, things change when I put a saturation block. So what I do here is, okay, let me add something here. This is what my controller computes as u prime, but because of saturation, my actuator can only deliver u. Okay, so this is what my control might demand 500, but my actuator can only give 300. Now let's say that, okay, let me put this number a little more liberal. Say this is say 1000, and say the limits here are like within 1000. Say my actuator can give whatever the controller asks it. But say in reality, my actuator has a limitation of say some 300. Okay, in that case, how will my controller respond? So my actual input that my controller computed could be something like this. This is my u prime, but what the u I can deliver is only until here. This is the u that I can deliver. Okay. Now because of this, my plant will of course move slower. So this is my reference. I can't move as fast. So this is what is desired with us. This is the speed that is desired, or this is a transient response that is desired. This is the rise time that is desired, and so on. I can't move fast. So my plant will move slower than actual. It will move slower, it will move slower, it will move slower, and reach this point, right? Not in a straight line, but say some slower behavior, because I can only pump in 300 RPM, even though my plant is maybe asking some 800 RPM, or my controller asks for 800 RPM. So in all this time, so this is my actual. This is my reference, and this is my actual. And you see how the error behaves. So I start with error here is one, error here. Uh, Error starts from 1 and it goes to 0 here. Okay. Similarly here, if I just were to plot, the error starts from 1 here and goes to 0 here. You see the integral of the error here and the integral of the error here. Here, there is a larger accumulation of the error. Okay, so once I am here, of those three control terms, Kp times E plus Kd times E dot plus Ki integral over E. Error is 0, this term goes to 0. And while we are reaching here, this is could be insignificant enough, so this time is also, it also could be 0, or very small enough to so that we can ignore. Look at this particular term. The accumulation in the former case is smaller, the integral of E, and this is much larger. So even though the error has become 0, the control law would still take it further, that the input command is still much larger here, because it is decided by the amount of error that is accumulated, and it will keep on accumulating until I go into this negative region, until my error, so this is the positive area, this is the negative area, until a point where then the error becomes, where the area becomes 0, the control becomes 0, and so on. Okay, so what we see here is, because of this limitation, you see a larger overshoot and a slower response. Okay, and this thing, what we see here, this is the integrator wind-up phenomena. Okay, let us take the example of the tank that we had in our initial lectures. So there is a little, say, some opening here for the tank, and QI, QO, the QI dot and QO dot regulate what is my height. Okay, so the control problem is to regulate to a certain height which is desired, say to some value where everything goes well. I have the H desired, my control input behaves like this, with and this is kind of driven by the valve opening. And let's say at some certain thing, this is my maximum valve opening, and say this is achieved by say valve opening of say about 80%. Okay, let's say something else happens where my output changes from, or this QO changes from QO to 3 times QO. That more water is kind of going out. In that case, what would I expect? Uh, to have the same response, my U prime now becomes, so this is close the 100%. My U prime now asks for 200% of the oil. So this is my U prime, whereas my actual will start here, and after this just becomes here. This is my U. This is what my actuator can deliver. Okay, so what will happen as we saw earlier, say this is my reference height. I start from here. The response, as we saw earlier, will be uh, kind of a little, we'll go till here and maybe reach a set point at possibly a little slower because of what we saw previously of how the response becomes slower and you see a larger overshoot. Now let's say once I reach this point, my QO becomes again from Q0, so 3 times Q0 to Q0. What would we immediately think is that my input now should go to the acceptable levels of what was here. But it doesn't happen because my error here, which is 0 at this point, keeps accumulating, and my actual, so this is my error, and the integral of E will be some value here like this, right? And this is now has taken a fairly large value. So even though my set point now has changed again from 3Q0 back to Q0, let's see how the error behaves. So there will be a little bit of negative error here. Let's say for the next 1 second, I go here, and because of this negative area, the integral of E will decrease. So maybe it decreases from say 2 till say zero point 0.8, sorry, 2 till 1.8. Okay, even at 1.8 now my motor will pump in, or my valve will be at its full opening. So valve which has its full opening, it still keeps on increasing until this area here, positive area, is nullified by the negative area here, and then it slowly starts coming down. Okay, so this again, this thing here is the integrator windup phenomena, where even though the actual output after a while the controller wants is only maybe 0.times the original, but it takes some time for it to realize that. Also, let's say I have a drone. I don't know how I'll draw this, but okay, in a very, and say I'm operating, somebody is operating the drone here with a remote in his or her hand, and say the idea is to get it to a height of say 10 meters, for which well, I have a certain input that needs to be okay. So for some reason something gets stuck and then the drone does not move, and this pilot is trying to control it from far. So this is my reference at the ground, uh, and the drone doesn't move. So what my controller will see is a constant error of 10 meters, and because the drone is stuck, it just cannot move, and my control input, or the error, it will just accumulate. It will always see like a constant error. The integral of the constant error will just keep accumulating like this. Okay, until someone spots it. So what happens is, so if under steady state, maybe it required a control say of zero point 0.8 of the full value, which could be the thrust that it resultant thrust that it generates. Now, because the error has accumulated, it might go up to say 3 times its original value, until somebody said, "Hey, the drone is stuck," and then you kind of remove the obstruction and it starts moving. Okay, now the drone starts moving to say, okay, I'll hide this person now. And the same kind of phenomena we will see. The drone starts moving now from 0 to moved to 10 meters. So this is when the obstruction is removed. And by the time the obstruction is removed, okay, let's draw it a little bit to scale here. Okay. So here, maybe at this point, somebody realizes that there is an obstruction, and the drone starts moving from here. And now the control U prime is now 3, okay, and the U is just 1, like the 100% of its full value, okay, and this starts moving, and by the time there is enough error accumulated here. Okay. Now there is enough error accumulated such that the control input is 3. Actually, it can deliver is 1. This is my reference value of 10 meters, and I still keep on accumulating the error until I reach this point. At this point, again, I'm at the desired height of 10 meters, where the actual control input required is what is computed because of the previous error accumulation is 3. It can only deliver 1, and it still keeps on moving further away from 10 meters. Because the error I accumulate, or if I just see the error kind of keeps accumulating because I cannot move, and the error now goes into the negative, right? So at this point, the error is 10. Now a negative area will start accumulating until the point where this thing cancels out this thing. So I'll keep on moving maybe until 20-25 meters until I start coming back. Okay, so that is largely the phenomena. So what is happening here is my drone is stuck. It does not move up, but my controller thinks it as an error, keeps on integrating the error, and asks me for more input. It tells the actuator to generate more input. So in this case, it goes to 300% of its total value. Until somebody spots it, you release the drone from whatever its obstruction is. It just starts keep moving up and up, goes to an error of goes to the 10% set point value. By the time there is enough error accumulated, now this error accumulated has to now be compensated by the negative error. So even though now I'm at this point, the controller now computes the difference of this positive and negative errors. It will maybe compute to 2.8, but my drone is still running at the full throttle. It will go to 2.0, 1.5 until it comes down to 1 and slowly goes down. It will still keep rising to say some 10 meters to say 15 meters. This is the concept of an integrator wind-up phenomena, which is due to the saturation of my actuator. In later design lectures, we will see how to actually control this phenomena, or how to design phenomena which will negate the effect of integrator windup. Those things will come up in the future lecture. So this lecture was largely devoted to practical aspects of PID control. Thanks for listening, and see you in the next week's lecture.